Complex data, such as computer communications and financial transactions, are difficult to analyse. Yet they can often be visualised as networks. Here, we're interested in anomalous structures in complex networks because they can indicate deviant behaviour. In this video, we explore what is normal and what is not, and how we can detect anomalies in networks. Here is a network with about 1,000 nodes. Let's zoom in on part of the network, and zoom in further. This subgraph still looks complex. Looking closer, we highlight a structure. Is this structure anomalous? How do the red nodes connect? Could this be an anomaly? Assuming that there's some natural random variability in the edges, we can detect anomalies statistically. Let's assume that we know the probabilistic mechanism generating the networks. We may not be able to easily calculate the probability distribution for the subgraph counts, but we can simulate networks using the same network model. If our structure is typical of the model, and we simulate many networks, we would expect to see it fairly often. But what if we simulate 999 networks and it doesn't appear? The observed network comes from the same model as the simulated networks, so we have 999 plus 1, or 1,000 networks from the model. This special structure appears only once in 1,000 networks, so its reoccurrence is highly unlikely. We can formalize this into a statistical test. Our null hypothesis is that the observed network comes from the hypothesized distribution. Our test statistic is the number of times the red structure appears. Say, for example, we generate 9 networks from the network model and count how many copies of the red structure appear in each one. We order these counts to see where our observed count of 1 sits within the sequence. Here, the observed count is the largest. Under the null hypothesis, all orderings are equally likely, so the probability that the observed count is the largest count is 1/10. Therefore, we reject the null hypothesis at the 10% level and conclude that there is an indication that the red structure is anomalous. This test is an example of a Monte Carlo test. It works as follows. From our observed dataset, we calculate a summary statistic, the observed value t0. We want to test whether the observed data can be explained as a realization of the null distribution, and we reject this hypothesis when t is large. So, we simulate a large number, n, of observations from the null distribution and calculate a summary statistic for each one, making up the sequence t1 to tn. We count how many of these simulated statistics are at least as large as t0. Let's say there are m of these. Then, under the null hypothesis, the probability of a value of t being at least as large as t0 is calculated. If this probability is smaller than a predefined threshold, we reject the null hypothesis. This test is not restricted to networks. It's useful when the underlying model is so complex that we cannot easily use it to make calculations. The cost action COSTNET consists of a collaboration of more than 500 researchers across 34 countries and is funded by the EU to carry out research into network data science. Our research is crucial to understanding and controlling infectious diseases, but also the stability of global financial networks, novel drug targets in genetic networks, underreporting in arms trade networks, as well as detecting anomalies in networks.